Okay, so welcome back. I got a question in chat, which was whether or not I could change how I was going to do the final uh, and give more time. The reason why it's probably a no-go is because there's certain restrictions we have on grading when it comes to finals and how quickly we're supposed to have it done. So and I know that some departments flaunt the grading deadlines after finals, but the math department usually doesn't. So if I do it this way, then you'll have plenty of time and you'll be done on the appointed day that you're supposed to be done on. So remember, this exam is not. I'm not making it longer, so it's not like as long as a general take-home exam might be. I'm just giving you a ton of time to do it, so it would be plenty feasible for you to sit down and do it in like an hour and a half, 2 hours on that day itself. This is just extra time I'm giving you. So even if you have other stuff that you have to get done or whatever, what I'm saying is that like this exam won't take you that long. Anyway, so last time we had no, I'm writing the final. Yeah, I'm writing the 461 final, so it's just me. Okay, so last time I had at least defined the singular value decomposition, and at least had described previously where these things come from. So the sigma is this m by n diagonal matrix here, where D is an actual diagonal matrix, and I've just kind of stuck it in a matrix. And then this looks like it's D and then one more row of columns and one more row of, or sorry, one one more column of zeros and one more row of zeros. But that's not how it is. That's why I have these things circled. So I have m minus r rows of zeros that I have to add in, and n minus r columns that I have to add in. And I have to add those in because otherwise this wouldn't be an m by n matrix, since D is actually an r by r diagonal matrix, where r is the rank of this matrix A that we're starting with. Okay. Um, so it can be very Sam, no, there's not an announcement with the info yet. I didn't make it over the weekend. I'll make it today. So I'll post a big final exam info announcement today, letting you all know how it's going. Well, or I should say, transcribing what I said last lecture that I would do. Okay. So anyway, it can be kind of confusing to keep track of all the stuff that's going into a singular value decomposition, right? So you have matrix A. Matrix A is some rectangular matrix n by n, so you can't talk really about technically diagonalizing the thing. But the idea is that you have matrix A, you look at A transpose A. This thing is symmetric, which that automatically guarantees it has a bunch of nice properties. We arrange its eigenvalues in this way, right? And once we do that, it has some number non-zero singular values. Well, it turns out that number of non-zero singular values is R, which is the rank of A. And these vectors, that is A multiplied by these eigenvectors of A transpose A, forms an orthogonal basis for the column space of A. Okay. All right. With all of that taken into account, the statement for the singular value decomposition is that we have an m by n matrix. It has rank R. There exists then an m by n matrix sigma, as I just showed you, okay, for which the diagonal entries in that small block matrix inside, or the small matrix inside that block matrix. I know that I haven't really talked much about matrix partitioning or block matrices, so we'll get to that on Wednesday. So the diagonal entries here are the first R singular values. of A, and those things are, we're calling them sigma sub 1 to sigma sub r. So these are, remember, these are the square roots of the eigenvalues of A transpose A. Right? And there exists an M by M orthogonal matrix U and an N by N orthogonal matrix V such that A is U sigma V transpose. Remember, it's an orthogonal matrix, so V transpose is the same as V inverse. So this is the singular value decomposition of A. Okay. Again, this is kind of a lot to keep track of. Going back one more page, right, to remind you of this. We start with A. A transpose A is symmetric. It can be orthogonally diagonalized because it's symmetric, right? In fact, those are exactly the matrices that can be orthogonally diagonalized. Then, because it can be orthogonally diagonalized, I have an orthonormal basis consisting of the eigenvectors of A transpose A. I have the associated eigenvectors. I can arrange those, of course, to be in this order, right? So descending order. They're all non-negative because of this fact, right? That actually every single eigenvalue is associated to some length squared. And so one way of thinking about the singular values is they are these lengths, right? But since these lengths squared are the individual eigenvalues for A transpose A, if I take the square root, then these lengths are the square roots of the eigenvalues here. And so these are what I call my singular values of A, and that's where the singular value decomposition gets its name. Okay. So going all the way back here. Big question. How do I find the singular value decomposition? So here's the thing, right? Singular value decomposition is not really going to be something that typically you're asked to do like immediately on the fly with no extra info, because it's kind of annoying and it's kind of complicated, unless the matrix involved is really, really, really small. Okay, so let's see how this works for a single example. Okay, so example. This is the big example that I promised, and then I'm going to get into how you can apply this in one of my favorite ways, which is talking about image compression. But there's a ton of applications of the singular value decomposition. Okay, so how does this work? So in fact, so let's find the SVD of the matrix A, which we used in an earlier example, either last lecture or the lecture before. So I'm going to actually read column-wise. 4, 8, 11, 7, 14, minus 2. So I didn't actually write out what the eigenvalues and eigenvectors of this thing were. I think just flashed it on the screen, but I'm actually going to write that out now. So I want to find the singular value decomposition of this A. Okay. So we find SVDs in 3 steps. Okay, that's kind of the way to deal with it. Okay, so what is the first step? So the first step is to find an orthogonal diagonalization of A transpose A. So find an orthogonal diagonalization of A transpose A. Now we can't fail here, right? In fact, you should note, just to remind you of why this is so nice, or one reason why this is so nice. What assumptions did I make on A? All right, so see if you can spot them. A has rank R, but I mean every matrix has some rank, right? So that's not really an assumption. This is just me saying that I'm letting my rank be called R, right? So what am I basically assuming about A? Nothing, right? Basically nothing. Okay, so I'm basically assuming almost nothing, right? I mean, it's just a matrix, right? It's an M by N matrix. That's what I'm assuming about A. Now, depending on what, like if this is the zero matrix, for instance, whether or not this is going to be more or less useful is up to you. But the idea is that singular value decomposition is a thing that I can do to every matrix. Okay, that's one of the reasons why it's so nice. Okay. So I want to find an orthogonal diagonalization of A transpose A. The reason I mentioned that before is that I can't fail this, right? So I can't fail this because A transpose A is symmetric. So I'm guaranteed that this works. But finding an orthogonal diagonalization, what does that mean? I.e., right, if I want to find an orthogonal diagonalization, what I need are the eigenvalues and the orthonormal set of eigenvectors, right? So find the eigenvalues and the orthonormal set of eigenvectors. Right. Okay. Now, the problem is that, of course, doing this, if you're, as we'll see in the next example that I give, typically you would want to do this for a pretty big matrix, possibly. Now, if this matrix only is pretty small, like ours, then we could do this by hand. But, this is going to be insanely horrible for a large matrix, right? Remember, finding eigenvalues itself, these are roots of polynomials. So the second that the degree of the polynomial is like 3, right, it's already more complicated. And so you can imagine trying to find the roots of some, degree 17 polynomial. It's not fun to do by hand. Okay, and so just that alone would make you run to the hills looking for some way to do this, computationally that's not a nightmare. And so, the examples I'm going to give of images, for instance, if you're storing if you're storing the data, right, like for an image pixel by pixel, then, if you have like a 300 by 200 image, then you're storing that as like a 300 by 200, matrix, right? That's the idea. So anyway, so that's if you're storing, for each pixel you have some number that's representing, say, color, right? Then these are going to be large matrices that you're dealing with. So anyway, let's say that. Let's say though that I don't put any of those computational concerns under what I'm doing. I'm just gonna do it. So I find the eigenvalues in an orthonormal set of eigenvectors. So we already have this for our A transpose A. Okay, so this was done in the textbook, in that example that I listed before. So what is A transpose A for us? So A transpose A, this is reading off row-wise. This is 4, 8, 11, 7, 14, minus 2 times A as above. So what is this? So if I multiply this out, which you can do if you want to, but I'm just going to write it out for you. Reading row-wise, this is 80, 140 in the first row. Second row is 100, 170, 140. And the last row is 40, 140, 200. I'm a little bit off the page. There we go. Okay. All right. So then, this is my A transpose A. What are the eigenvalues of this thing? So eigenvalues of A transpose A. I'll go ahead and put them into nice order here. So these are lambda sub 1. This is the largest eigenvalue. That's 360. Lambda sub 2 is the next largest eigenvalue. That's 90. And lambda sub 3 is 0. Okay. Those are my three eigenvalues. Okay. Now, so there's my three eigenvalues. I need some unit eigenvectors to go with those. So corresponding unit eigenvectors. What are those? So I have V1 associated to lambda 1. That is 1/3, 2/3, 2/3. That's V1. V2 is minus 2/3, minus 1/3, 2/3. And V sub 3, the one associated to 0, is 2/3, minus 2/3, 1/3. There you go. Okay. All right. And so, what do I do here? Right. Well, now that I have those, my idea is to set up V and sigma. Okay, so I have an orthogonal diagonalization. I'm not going to write out the diagonalization because I know that in order to diagonalize, this is all I need. So the diagonal matrix in question would have diagonal entries 360, 90, 100, right? And that is the diagonalization for A transpose A. So its diagonal entries would be 360, 90, and 0. So 360, 90, and 0. And so the matrix P, right, that diagonalizes it would have these as its columns, right, in that order, right? So first column, second column, third column. Okay. All right, so that's my first step done. All right, because I just had that info at the ready. Okay, so step 2. Okay, so step 2 is set up V and sigma. All right. So remember, the thing that I'm trying to do here, maybe I'll just write it up here in the upper corner, right? The thing that I'm trying to do here is to set up a factorization of this A that looks like this. Right, U sigma V transpose, where U is an n by n orthogonal matrix. V is an V is n by n, and U is m by m. Right. Okay, and sigma is m by n. Okay. So maybe I should have given myself more room here, right? Actually, let's make this cleaner. So what we want, right, is a matrix A that factorizes like this. And U is m by m, sigma is m by n, V is n by n. That makes this multiplication work out just fine. And remember, A is m by n. Right. So A is a generic m by n rectangular matrix here. And U and V are orthogonal. So these are square orthogonal matrices. And sigma is this weird block matrix that looks like this. Okay. All right. So that's the really quick write-up of what it is, we hope to do. Okay, so then the next thing is we want to set up V and sigma. Now, how do we do this? So, in general, you would arrange the eigenvectors in decreasing order. Well, the eigenvectors are vectors. They don't really have an order on them. So then what do I mean by decreasing order, i.e. Corresponding to the eigenvalues? Okay, so you can't really talk about order on vectors, right? It doesn't really make sense to say one vector is bigger than another. The idea, though, is that they're associated eigenvalues, which in this case are going to be real numbers that are going to be non-negative, and I can absolutely talk about an order on non-negative real numbers. Yekta, yes, A is M by N. Sorry, that might not be. That might look like an N. A is M by M, or M by N. So A is an M by N matrix. Yes, that's right. Okay. And that's what's nice about all this, because this can be applied to any matrix you come across. Okay. So I'm going to arrange the eigenvectors in decreasing order. That's the first thing. So in this case, it was already done for me. So I already arranged them in decreasing order. Where did I put my paper I was just writing? Oh, there we go. Yeah, so in my case, it was already done for me here. So there's my eigenvectors in decreasing order. There's the associated eigenvalues. Okay. Okay. So then, right, the eigenvalues I've already listed, right? Lambda 1 is 360. Lambda 2 is 90. And lambda 3 is 0. Okay. So the corresponding unit eigenvectors v1, v2, and v3 are the right singular vectors of A. So people asked in chat, at least one person asked in chat last time, what the significance of the right versus left singular vectors were. So this is telling you exactly that the right singular vectors are the unit eigenvectors of A transpose A. So that's where these come from. So these are my columns of V here. Okay. So these are the right singular vectors of A, and so V is the matrix with columns v1, v2, v3, which, as I listed on the previous page, comes out to be column-wise: 1/3, 2/3, 2/3. Next, minus 2/3, minus 1/3, 2/3, and 2/3, minus 2/3, 1/3. Okay, so there's my V. Okay. How do I find the singular values, right? So next I compute the singular values, because I need the singular values to write sigma. So here's V. So I'm almost done with this step. I have set up V. Now I just need to set up sigma. So now I compute the singular values of A. But what are the singular values of A? Well, the singular values of A are the square roots of these eigenvalues, right? So sigma 1 is the square root of this lambda 1, which is square root of 360, which is 6 root 10. Okay. And this is, or sigma 2 is the square root of 90, which is 3 root 10, right? So this is square root of lambda 2. So this is square root of 90, that's 3 root 10. And then the third singular value is 0, right? So it's square root of lambda 3, which is 0. Okay. All right. So now what? Now, remember, this sigma is some block matrix that has D as a matrix inside of this R by R diagonal matrix. So what are the entries of D? So D is the diagonal, so D has diagonal entries that are the non-zero singular values of A. Okay, so what do I have for my matrix D and sigma? So then D is the matrix 6, root 10, 0, 0, 3, root 10. Yeah, so D is a 2 by 2, right? And it's 2 because the rank of A is 2, right? Note the rank of A is 2, so D is 2 by 2. Okay. But of course, what is sigma then, right? So remember, sigma is this thing, right? D, and I'm writing it like this, but of course what we mean here is what I had written before, which is that we have how many 0 columns? Well, we have n minus r of those. And how many 0 rows? We have m minus r. Okay, so does this sigma need any 0 rows? That is the question, right? Well, how many rows does this sigma have? Well, sigma is going to need to be the same size as A for this to work out, right? And so because of that, I'm not going to have any 0 rows here, right? So I'm not going to have any 0 rows here. I'm going to have 1 0 column added in. And so for us, this sigma is equal to D with a 0 row added in, which is the matrix 6, root 10, 0, 0, 0, 3, root 10, 0. Okay. Now, like, why did you know that this had to work out like this? Right? So why did you know that this had to work out like this? Because you know that sigma is going to have to be the same size as A, because this A has rank 2, so it forces this D to be 2 by 2. Sigma is not going to be bigger than A. And the way that this has to work, it has to have 3 columns so that it can multiply on the right by V transpose, right? So this nails down how big sigma has to be. You can also just compute it from this picture. Let's see what the thing, what is said in the chat. Is this step 3? No, this is still step 2. Yeah, and so Gustavo, as Gustavo said, it's 2 by 2 with sigma 1 and sigma 2 on the diagonal. So that's what D is. Yeah, and I'm still in step 2. In general, is the eigenspace corresponding to an eigenvalue of 0, the null space, that matrix? Yes, that's right. That is true. Okay. All right. So we have found sigma, and we have found V, which means we found V transpose, because we understand how to transpose a matrix. Okay, so our second step was to set up V and sigma. So just to remind you, there's V. V just came directly. Its columns are the unit eigenvectors in the right order, right? So the descending order. These are my right singular vectors, or just the columns of this V. Okay, so I got that from my previous info of the eigenvectors and eigenvalues for A transpose A. Okay, so from that same info, I compute the singular values. I just take the square roots of the non-zero. Okay, so I need all of the singular values, so I'll go ahead and find them. So I can take square root of all these eigenvalues. I get my singular values. To form D, and thus to form sigma, I only need the non-zero singular values. So there they are. Here's sigma. So we have found both v and sigma. So we're almost good to go. All right. We didn't have the zero eigenvalue in D because D is only ever made up of the non-zero singular values. Okay. So the non-zero singular values are all that is contained in D. D never has zero singular values. Okay, and so we have one more step. Step 3. Okay. This is constructing U, right? Because, I mean, to come up with the singular value decomposition, we need U, sigma, and V, right? So we've constructed sigma and V, but not U, right? So construct U. So where does U come from here? Okay. So when A has rank R, how do I get U? The first R columns of U are the normalized vectors. So these are the normalized vectors obtained from AV1 to AVR. Okay. All right. Remember, as a result of this whole construction process, those vectors are guaranteed to have some nice properties, right? They're guaranteed to be an orthonormal basis for the, well, the normalized versions of those, guaranteed to be an orthonormal basis for the column space of A. Okay. All right, so you should, that was the theorem that immediately preceded the singular value decomposition. Okay. Here, rank A is equal to 2. Okay. So, and also recall that, let me take you back for a second, way back, well, I mean, just back to last lecture. When we were first doing the definition of the singular values of a matrix, right? So that's what's being defined here, singular values of a matrix. We did this computation that showed that each of these eigenvalues was actually the length of these AVI vectors squared. Okay, and this is how we defined the singular values, right? So another way of viewing the singular values is that they're actually equal to the length of these AVIs. Okay? And so going back here, since I know that the length of AV1, for instance, is sigma 1, and the length of AV2 is sigma 2, all right? Thus, if I'm writing up columns of U, my first column of U is going to be 1 over sigma 1 times AV1. So this is just me scaling the vector AV1 by its length. All right, that's all I'm doing here. So this is 1 over 6 times root 10 times AV1. So I have to compute what that is, but I'm just going to write out what it is here. So A times V1 is 18.6. Okay. And so this vector is 3 over root 10, 1 over root 10. Oh, so the thing is that the way that we want to do this is, so here's some of the intuition for why we would want to put them in decreasing order. So one thing, we can always do this when you have eigenvalues, that are all guaranteed to be real. You could always do this, and from the diagonalization process, it doesn't matter what order you list the eigenvalues in the diagonal matrix, as long as you change the order of the eigenvectors in as they show up in columns of the diagonalization matrix P. You can do that. You can put them in any order you want to, right? Anyway, one reason, right, one intuition is, or one part of the intuition for why you might want to do this is think about what we did with maxes and mins, right, in the constrained optimization problems. So in the constrained optimization problems, basically we saw that the largest eigenvalue corresponded to the max and the smallest to the min. And if you threw in additional constraints that basically zeroed out or said that you were orthogonal to, like, say, the first eigenspace, if you've listed them in decreasing order, then the new max relative to those constraints was the next largest eigenvalue, right? And so on. And so that's one really good reason why the constrained optimization stuff is one really good reason why you would always want to do this if you could. But also for the singular value decomposition, doing it this way means that you can say a lot of nice things. Like, for instance, the main thing that we're going to say is that, like, the first 5 eigenvalues contain like 99% of the info, right? Or maybe I should, instead of saying eigenvalues, I should say like the first 5 non-zero singular values, are going to contain, in some instances, like 99% of the actual data I care about in some potentially huge matrix, right? So I could have like a 100 by 100 matrix that has, a ton of singular values, right? It's going to have a long list of singular values, but maybe only the first 5, the largest 5, are the ones that I care about. Because remember, those are telling me a maximum, or they're telling me a direction in which the max is obtained in some sense. So that's the intuition for why that you would want to do this, okay? And so we just do this because it makes everything nicer rather than having the eigenvalues strewn about in just some random order, right? There's no benefit to that, right? Okay, so there's no benefit to having eigenvalues just listed in whatever order you want to, okay? Okay, so the other U vector here is 1 over sigma 2 times AV2, which is 1 over 3 root 10 times the vector 3 minus 9. And this is the vector 1 over root 10 minus 3 over root 10. Oh, there we go. Okay. Okay. So here's something. This is already a basis for R2. Right? This is already a basis for R2, so I don't need more vectors for U. In general, right, I may need to come up with more vectors for U, and the way that I could do this is basically extending a set to an orthonormal basis for R3. And so what you would do there is Graham-Schmidt. But I'm not going to get into that because, like I said, I'm not going to give you an example of anything like that. Right? So at this point, so since U1, U2 already form a basis for R2, I don't need any more vectors. So typically here, as I said, you would have to do more, right? So typically, we may have to do more here. i.e. like extending the above to be a basis for R3 or whatever, right? I mean, in the case that the dimensions were different here. Okay. So I don't mean taking these vectors and making them a basis for R3. What I mean is that you may end up with a set of two vectors in R3, and you need three, right? So you like from this process. Notice that at the beginning of this step 3, I said when A has rank R, the first R columns of U are the normalized vectors you get here. You're not always going to have enough, though. Okay. How did I get the length of AV vectors? That comes from the original computation of the SVD. When I was first defining singular values, I noticed that because these were eigenvalues and eigenvectors of A transpose A, the length of AVI squared is this thing, right? Writing out exactly what this is, I get that these eigenvalues lambda I are equal to these to the length of AVI squared. Okay, and so another way of thinking about this is the sigma sub i's are the lengths of these AVI squares. That's where I'm getting that. Okay, so anyway, you may have to do more here that might involve Graham-Schmidt and things like that, but I'm not going to go down that path because I really just want you to see this full example, and then I'll talk about applications because I'm not going to give you like a really, really long SVD or anything on the final. Anything I ask you about the SVD would be, purely conceptual. Okay, and so I'm almost done here. Now I just need to form U. So thus, U is the matrix that has columns U1 and U2. And so we're done with step 3. And I can write A is the matrix 3 over root 10, 1 over root 10, 1 over root 10, minus 3 over root 10. This is U times a matrix sigma, which is 6 times root 10, 0, 0, 0, 3 times root 10, 0, times a 3 by 3 matrix, which is 1/3. I'm going to read column-wise, so 1/3 minus 2/3, 2/3, 2/3, minus 1/3, minus 2/3, and 2/3, 2/3, 1/3. All right. Okay, and so this is my U, this is my sigma, and this is my V transpose. Okay. And if you really wanted to check to multiply those out, you would see that those are equal to A, which we said was 4, 11, 14, 8, 7, minus 2. Okay. So there's the singular value decomposition. Again, you might have to work a little bit harder for U than we did in this particular example, but this is just showing you kind of a general idea of how this goes. Now, what I wanted to mention is some applications. So the book has some applications, and they're pretty good, but they're not my favorite, so that's why I wanted to talk to you about some applications of the SVD. All right. Okay. And so, Gustavo, you're saying you might not have. So the issue is that A might not have full rank, right? So A has full rank in this case, right? But if A were, say A didn't have full rank, right, then the vectors you get wouldn't be big enough to make up the difference, right? You'd be missing something. So that statement, the theorem that we have before the formulation of the SVD, says that those AVI vectors give you an orthogonal basis for the column space of A. But A could definitely be, for instance, like take it. What if our A had like rank 1 or something, or say you had an A that was like 3 by 4 and it had rank 2, right? Then you're going to end up with issues, right? So U is not going to be the right size in that case, right? So U has to be big enough. You're not going to have enough columns in U if A doesn't have full rank. So anyway, that's the deal. Okay. So, what's going on here with the applications of the SVD? So this is my favorite example. So some applications of SVD, I'll say that there are a ridiculously huge amount. Of these. So there's no possible way I can exhaustively cover these. In fact, if you take Math 401, and if you take Math 401, you will see very, very many applications of SVD. In fact, you might spend a few weeks just on applications of the SVD. Okay. So then the image compression example is one of my favorites. So what is the idea here? The idea, so we store image data in some matrix, right? Call it A, where the matrix in question, so we do this pixel by pixel. And so if we are storing image data in this way, then what are some typical approaches? So what we could do, so here then my M by N, right, represents the pixel count, right? The vertical and horizontal pixel count. And so one example is for a color image. We could store each color value, right, as an integer between 0 and 255 included for 3 types, right? Red, green, and blue. All right. All right. So you could do that, but so doing this, I would need an R value, a G value, and a B value for each of these things. So for each of these things, I would get an integer value, right, which would give me a ton of combinations and would obviously allow for to store all kinds of things. But to make this simple, I'm going to focus on, like, say, Grayscale Image, right? So rather than having these 3 values, which I could do, I could have Grayscale. So I could have, why did I spell it like that? So Grayscale Image, where each pixel is stored as a single integer between 0, and 255. All right, I could do that. Okay, so this is simpler, right? Where 0 is, 0 is black and 255 is white. All right. That's something I could do. I could do something really, really simple, right? So simple, i.e. black or white. So each pixel is stored as 0 or 1. Right, I could do that just as well. Okay, where 0 indicates black and 1 indicates white. All right, so there's a lot of options here, but the point is that so for instance, if I wanted to have an image and I knew its its pixel size, so if it was 300 by 200 or something, then I could form a 300 by 200 matrix, and each entry in that matrix would be an integer between 0 and 255, where 0 represents a completely black pixel and 255 represents a completely white pixel. So in that way, I could have a grayscale image, right? Okay, so what is then the idea? And I'll talk a little bit more about this since I'm running out of time here. So the idea is I can find the SVD of my image matrix. Okay, so I can find the SVD of my image matrix here. And it turns out that in many cases, I can toss out data that is less important by identifying how or where the important data is. Okay. Now that seems very hand wavy because there's a rigorous thing I will say for each of these quoted phrases. But the idea here is that the SVD is going to tell me basically which parts of that matrix are important. So it's going to allow me to basically take my image, toss out some data that is less important, and keep behind an image that has been drastically reduced in size in many cases, while being extremely similar to the image that I started with. Okay, this is the notion of image compression, right? That's the idea. The idea is you take some image, and as it is, just the raw data, it's too much data, it's too big. But it turns out, what you care about, how the image looks. In some cases, you can reduce, the size of this image by, you can reduce the size of the data by a huge amount while keeping the image looking almost the same. Okay, so this is very, very important for a variety of reasons. Evan, the thing is that for more complicated ways of storing like color data, then you can do. There's other things that you can do. But for grayscale images, this works fine. Storing grayscale images, each pixel between 0 and 255, this works perfectly fine. Which is why I'm not going to do any examples of RGB stuff. I'm just gonna do this one example to show you what happens in the case of grayscale image. So I'll do that quickly. I'll talk about Jordan canonical form, maybe get to the Hadamard matrix conjecture if I have time on Wednesday, and then I'll try to leave most of Friday and Monday for just random questions. So that's the idea. So let's see. Is that why image operations scale up exponentially with resolution? I have to think about that for the SVD's case. It's possible for for the case of applying the SVD. How's that going to be how's that going to be affected? I have to think about it a little bit more. Anyway, so that's the deal. So I will see you all on Wednesday. I'll make an announcement about your final last time, but remember, you're going to be done with the entirety of this course by your, like, when your final date is over, when 11:59 on, what did we say it was, the 17th or whatever, when that is over, you will be done with your obligations for this course. So that's the intention. So anyway, that's how it goes. I will see you all on Wednesday.